KVA and KW represent different aspects of electrical power. KVA, or kilovolt ampere, refers to the apparent power in an electrical circuit. Apparent power is the total power being handled by the circuit. It includes both active power, which is KW, and reactive power, which is KVAR. KW, or kilowatt, signifies the active power in an electrical circuit. Active power represents the actual power being consumed by the devices connected to the circuit. KVA is measured in kilovolt amperes, while KW is measured in kilowatts. To calculate KVA, you multiply the voltage in volts by the current in amps. To calculate KW, you multiply the voltage in volts by the current in amps and then by the power factor. KVA is always greater than or equal to KW. The difference between KVA and KW is the reactive power, kVAR. They are listed differently because they represent different aspects of electrical power. KVA represents the total capacity of the electrical system to handle power, including both active and reactive power. It is important for sizing electrical components such as transformers and generators. KW represents the actual power being consumed by the devices in the circuit. It is important for calculating energy consumption and billing. In summary, KVA is a broader measure of apparent power that includes both active and reactive power, while KW is a specific measure of active power only. It is essential to understand the difference between these two terms in electrical engineering. Reactive power is the portion of electricity that establishes and maintains the magnetic and electric fields in devices like motors and transformers. It does not perform real work but is necessary for the operation of these devices. The power factor is the ratio of real power, KW, to apparent power, KVA. It indicates how effectively electrical power is being used. A power factor of 1.0, or unity, means that all the apparent power is being used to perform real work, while a lower power factor indicates that a portion of the apparent power is being used to sustain magnetic or electric fields. Improving the power factor can reduce energy costs and improve the efficiency of electrical systems. Utilities often charge industrial customers for low power factors because it increases the burden on the electrical grid. Power factor correction can be achieved by adding capacitors to the electrical system, which supply reactive power and reduce the amount of reactive power that must be supplied by the utility. Transformers are rated in KVA because their capacity is limited by heating, which is proportional to the square of the current. The current is determined by the apparent power, KVA, not just the active power, KW. Therefore, it is important to select a transformer with a KVA rating that is sufficient to handle the total apparent power of the load. Generators are also rated in KVA for the same reason as transformers. The generator must be able to supply both the active and reactive power demanded by the load. If the generator is overloaded, it can overheat and be damaged. Understanding the relationship between KVA, KW, and KVAR is crucial for designing and operating electrical systems efficiently and safely. Proper sizing of electrical equipment, power factor correction, and accurate energy consumption calculations all depend on a clear understanding of these concepts. Reactive power is often associated with inductive loads such as motors and transformers. Inductive loads cause the current to lag behind the voltage, resulting in a lagging power factor. Capacitive loads, on the other hand, cause the current to lead the voltage, resulting in a leading power factor. By adding capacitors to the electrical system, it is possible to offset the effects of inductive loads and improve the power factor. Power factor correction not only reduces energy costs but also improves the voltage regulation of the electrical system. Poor voltage regulation can cause equipment to malfunction or operate inefficiently. In addition to capacitors, other methods of power factor correction include using synchronous condensers and active power factor correction devices. Synchronous condensers are synchronous motors that are operated without a mechanical load. They can supply reactive power to the electrical system and improve the power factor. Active power factor correction devices use electronic circuits to control the flow of reactive power and maintain a high power factor. The choice of power factor correction method depends on the specific characteristics of the electrical system and the desired level of power factor improvement. It is important to consult with a qualified electrical engineer to determine the best solution for a particular application. Electrical codes and standards, such as the National Electrical Code (NEC), provide guidelines for power factor correction and the sizing of electrical equipment. These codes and standards are designed to ensure the safety and reliability of electrical systems. Compliance with these codes and standards is essential for avoiding electrical hazards and ensuring the efficient operation of electrical equipment. When calculating the KVA of a three-phase system, the formula is KVA equals the square root of 3 multiplied by the voltage in volts multiplied by the current in amps, all divided by 1000. For a single-phase system, the formula is simply KVA equals the voltage in volts multiplied by the current in amps divided by 1000. Similarly, for a three-phase system, KW equals the square root of 3 multiplied by the voltage in volts multiplied by the current in amps multiplied by the power factor, all divided by 1000. And for a single-phase system, KW equals the voltage in volts multiplied by the current in amps multiplied by the power factor divided by 1000. These formulas are essential for accurately calculating the apparent and active power in electrical systems. The power factor is typically expressed as a decimal between 0 and 1. A power factor of 1 indicates that the voltage and current are in phase, and all the apparent power is being used as active power. A power factor less than 1 indicates that the voltage and current are out of phase, and some of the apparent power is being used as reactive power. The power factor can be measured using a power quality analyzer. A power quality analyzer can also measure other electrical parameters such as voltage, current, frequency, and harmonics. Harmonics are distortions of the sinusoidal waveform of the voltage and current. They can be caused by nonlinear loads such as electronic equipment and variable frequency drives. Harmonics can cause a variety of problems, including overheating of equipment, malfunction of electronic devices, and increased energy losses. Power quality analysis is essential for identifying and mitigating power quality problems. There are various methods for mitigating harmonics, including using harmonic filters, line reactors, and shielded cables. Harmonic filters are designed to block specific harmonic frequencies. Line reactors are inductors that are placed in series with a load to reduce the harmonic current. Shielded cables can reduce the amount of electromagnetic interference caused by harmonics. The selection of the appropriate harmonic mitigation method depends on the specific characteristics of the electrical system and the type of harmonic distortion. It is important to consult with a qualified electrical engineer to determine the best solution for a particular application. In addition to power factor and harmonics, other power quality parameters include voltage sags, voltage swells, and transients. Voltage sags are temporary reductions in the voltage. Voltage swells are temporary increases in the voltage. Transients are short duration, high amplitude disturbances in the voltage or current. These power quality disturbances can cause equipment to malfunction or be damaged. Uninterruptible power supplies, or UPS, can provide backup power during voltage sags and outages. Surge suppressors can protect equipment from transients. Proper grounding and bonding of electrical equipment can also help to mitigate power quality problems. Grounding provides a path for fault current to flow back to the source, which helps to protect people and equipment from electrical shock. Bonding connects all the metal parts of the electrical system together, which helps to equalize the voltage and reduce the risk of electrical shock. Understanding and addressing power quality issues is essential for ensuring the reliable and efficient operation of electrical systems. Power quality problems can cause significant economic losses due to equipment downtime, damaged equipment, and increased energy costs. By implementing appropriate power quality solutions, it is possible to minimize these losses and improve the overall performance of electrical systems. When selecting electrical equipment, it is important to consider both the KVA and KW ratings. The KVA rating determines the maximum apparent power that the equipment can handle, while the KW rating determines the maximum active power that the equipment can deliver. It is important to select equipment with KVA and KW ratings that are sufficient to meet the demands of the load. Overloading equipment can cause it to overheat and be damaged. It is also important to consider the power factor of the load when selecting electrical equipment. If the power factor is low, the equipment may need to be oversized to handle the reactive power. For example, a motor with a low power factor may require a larger KVA rating than a motor with a high power factor. In addition to the KVA and KW ratings, other important factors to consider when selecting electrical equipment include the voltage, current, frequency, and temperature rating. The voltage rating must match the voltage of the electrical system. The current rating must be sufficient to handle the current drawn by the load. The frequency rating must match the frequency of the electrical system. The temperature rating must be suitable for the ambient temperature in which the equipment will be installed. It is important to consult with a qualified electrical engineer to ensure that the selected electrical equipment is appropriate for the intended application. Proper selection and installation of electrical equipment is essential for ensuring the safety and reliability of electrical systems. Failure to select and install electrical equipment properly can result in electrical hazards and equipment damage. KVA is also used in determining the size of generators for both prime and standby power applications. For example, a generator might be sized to provide power to a building during a power outage. The generator has to be capable of providing the total apparent power required by all loads in the building, not just the active power. This ensures all equipment runs smoothly without overloading the generator. Consider a scenario where a commercial building needs a backup generator. The building's total active power, KW, requirement is 200 kilowatts, and the average power factor is 0.8. To find the required generator KVA, you would divide the KW by the power factor. In this case, 200 kilowatts divided by 0.8 equals 250 kVA. So, the generator should be rated at least 250 kVA to handle the building's power needs. If only the KW was considered and a smaller KVA generator was selected, it would likely be overloaded due to the reactive power demands, causing it to fail or not operate efficiently. Another application of KVA is in the sizing of uninterruptible power supplies, UPS systems. UPS systems are used to provide temporary power to critical loads during power outages, and are often found in data centers, hospitals, and other facilities where continuous operation is essential. Like generators, UPS systems are rated in KVA because they must supply both active and reactive power. The UPS system has to be sized to handle the total apparent power of the connected equipment. Let's say a data center has servers and networking equipment that consume 150 kilowatts of active power with a power factor of 0.9. To determine the required UPS KVA, divide the KW by the power factor. In this case, 150 kilowatts divided by 0.9 equals approximately 167 kVA. Therefore, a UPS system with a rating of at least 167 kVA is needed to support the data center's equipment during a power outage. Choosing a UPS with only the KW requirement in mind might lead to an undersized system that cannot handle the total load, causing the data center to shut down during a power failure. The power factor is crucial in understanding the efficiency and cost-effectiveness of electrical systems. A low power factor indicates that a significant portion of the apparent power is being used to support reactive loads which do not perform useful work. This results in increased current flow in the electrical system, leading to higher energy losses in the form of heat, and also reduces the overall capacity of the system. Utilities often charge customers with low power factors additional fees because it strains the electrical grid. To improve the power factor correction techniques are used, which involves adding capacitors to the electrical system to offset the effects of inductive loads. By improving the power factor, businesses can reduce energy costs, improve the efficiency of their electrical systems, and avoid penalties from their utility providers. In summary, KVA represents the total apparent power in an electrical system, taking into account both active and reactive power, while KW represents only the active power that performs useful work. Both are essential in electrical engineering for equipment sizing, energy management, and ensuring efficient and reliable operation.